Creating an OS, Part 1. I'm going to create an operating system called InfernoOS to signify how unusable it'll be. This will be a tutorial on basic steps of creating an operating system. An operating system, OS, is system software that manages computer hardware and software resources and provides common services for computer programs. The operating system acts as an intermediary between programs and computer hardware. Oh yeah, and you'll need to build something called all this for an operating system. An operating system. One of the greatest discoveries known to man that we'll be attempting to do. Before we start with our bootloader, which was step part 1, we should experiment on what an operating system actually does. Before the operating system, there's something called the BIOS, which will instruct everything and do very basic computer functions before there's anything to actually do that. The operating system is just sleeping. Then the BIOS tells the operating system to giddy up, and the operating system starts running into the modern state that it is. And then the BIOS just sleeps, and the operating system is doing all the work. Wait, let's rewind. Remember the BIOS was telling the operating system to giddy up? Well, the BIOS can only run a small portion of the OS, the first sector with 512 bytes. That's an insanely small amount of code, not the simplest operating system could fit inside of there. So this is why we have something called a bootloader. Instead of actually being the operating system, the bootloader will ask the BIOS to read the next 6 sectors of the hard disk and run it. Keep in mind, the other 6 sectors are the rest of the OS. And the BIOS will just take those and run it, and the bootloader will just disappear. And then the operating system will be ran, and the BIOS will also just say goodbye when the operating system has everything. So yeah, that's the actual modern state of any operating system. So we're going to be doing all of this from the scratch. So first we need an executable that will be ran. Actually first we need the code to run. So I'm just going to create nothing in this file. And we're going to run it with a 16-bit mode. And output it into main.bin. And then we're going to be running the Creamer system i386 on that main.bin. And if you just give it some sufficient permissions, first you need to download Creamer, by the way. It actually will throw errors, and that's because we're not booting anything and we're not doing anything. So the first thing we need to do is we need to move do this. So actually I'm not going to write it yet. I'll explain it to you later. So okay, we created a basic main entry point, and now let's actually get to this org. So essentially the reason we're using this org is because this is my basic reason, even I don't know, but I think it's because the BIOS loads sectors to that region in the memory, from that region to the region in the memory. So we don't want any labels going there, because then it's going to think the start function is the stuff that we're trying to load, and it's going to think it's a kernel that we need to run, and it's going to run itself, and we're going to have a recursive loop, which we don't want. I hope we don't want. Anyways, essentially, what we're gonna do is we're gonna read into the next bytes, right? But in order for there to be next bytes, we need to actually make those next bytes. So we need to create a 16-bit thing, and its org is actually going to be different because we're in the kernel. We don't care about it overlapping. This is sectors we want to run. I'm actually going to change it to this because it's going to be Yeah, that's where we want to put it. It's in the hard drive. Placed in the hard drive. And anyways, now we're actually going to be adding the kernel to a build script, and we're going to do that. And then we're actually going to merge these two together. So let me call this bootloader bin for a second. And we're going to merge these two into one single main.bin. Then we're going to run that main.bin. So yes, it still fails, but the good thing is it's not coming from the creamer. It's coming from because we didn't have any code. So in order to read into the future regions, we need to call the BIOS using the int instruction until we want 0x13. Now, int 0x13 is the BIOS interrupt for providing sector-based hard disk and floppy disk read and write services. Right, so let's go. Now, what do you want to do? We want to read the first hard disk, so we can tell the DL is going to be 80H from that. And actually, before any of that, we need to create something like this. And I don't even know if that'll run. Yeah. So let's do that. And right after this, we need to put AA55 which will tell the BIOS it can run this disk. Now we're doing 510 here because I told you a sector is 512 bytes, and we have these 2 bytes right after, and this will essentially point to the start of the entire program, I believe. So yeah. So I actually found the code. It's this. I'm assuming this is the current relative address and this is the starting address. Yeah, that makes sense. So we can tell the BIOS that it can run this disk. And this is actually going to be in DL, so we want to move it there. And AH is going to be what we want to do, and we want to read sectors. So AH is going to be 0x02 easy. And then we have AL, which is the amount of sectors to read. Yeah, so we're going to read just one sector. And we're going to be starting from this place. This is where code's going to be starting. Right here, easy. And right here, you just want to jump here to make sure that is CX00. And it boots from the hard disk. It just says that. That means it's actually working. So now we want the BIOS to actually print something to our screen to commemorate the victory. So we're actually going to need an int 0x10, which will provide video services, I've heard. So yeah, that's pretty cool. Right here we can give the start int 0x10. Okay, cool. We're just going to move the AH. We want a tell type input. So that, and that actually means hex, so we're going to do that. The AL will be whatever character you want to print out. And that doesn't work yet. Because first we have to switch to the text mode. I'm actually curious, would this actually work? I'm just trying to check if it'll properly clear the screen. So that's kind of interesting. We want to jump to the start. Or we can CLI and hold. Right, okay. So now let's try doing the 0, 0 thing. It still doesn't work. Could we do start? Yeah, maybe she does not like me. So let's see what's wrong. The best level of programming is realizing that you forgot one argument. Yeah, everything worked. Anyways, we can print characters onto the screen. That's actually step 1 of the bootloader, which is to boot basic things. We have letter H. Boom. And I mean, it was a little bad, so I should have known it all, but like I needed a little medium. But anyways, it's time for step 2. Our first step was the bootloader, and we completed it. What's our next one? Basic kernel. So I already created a basic kernel by putting a letter, but I'm going to extend it to actually putting an entire string this time. I have the code copied in my clipboard. I'm going to give a quick glimpse of that. Right there. So we can create a string, which is hello world. First. So this is a string that we want to print. Right, and I didn't do anything. It still points H, right? And then we can create a function that will do exactly what this does. I'm not going to use my call on the clipboard because I don't want to. Yeah. So then we'll be doing the vet instruction. And it actually prints a ton of characters because we have to jump to start at the beginning. Yes. So now we want to print a string, right? So we're going to move this string into the SI and print A. And now we're going to print the first character of the string, H. The first character of the SI, same thing, H. If we increment the SI, it's going to be the next character. That's where I'm going with this, by the way. So as soon as we go into the thing, we're going to start into a loop. And we'll also have a done to the loop right here. So here, we'll just increment the SI and loop. Here we're gonna move the CX to be 6, so I'll put 6 characters of the string. And as you can see, that works. The problem is, we can't have a CX. So what we're gonna have to do is we can jump to the loop here. But that would be an infinite loop. So I think we actually have to check here. So see if it's 0 and J and E done. I think it's actually JE done. And that actually works. That was the quickest speed run I've ever heard of. 3 minutes. We put it a string. Let's compare it. Dang, it was pretty much the same thing. I mean, well, same purpose, different structure. But anyways, that's the first step of creating a minimalist kernel. Bum 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 bum. Dun 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 dun. What's next? graphics or something. Wait, I discussed it. Graphics. That's what we're gonna be having to do. And I'm actually going to look at an example of mine that I did right before this project. Right, you probably already saw it in tiny glimpses. But this is my example. I learn best from examples. I'm that type of person. So, anyways, I'm gonna call this a utils section. So all these utils are gonna stay there. They're still gonna stay there. Right? So here we are. We put our utils and stuff like that. And today we're gonna be drawing a point onto the screen. Because we chose to do graphics. So the first thing we want to do is we want to initialize the graphics mode. We're going to be using a different setup. There are multiple setups, and each have their own resolutions and different colors. We're going to be using a setup with a great resolution and a large amount of colors. I forgot its name. But now we actually have to write a point. So the way you do this is you could use N0x10, but I'm going to use stars B. And stars B will it's like saying in C, times di something equals A, or di is equal to A, depending on the circumstance. I think it's times di equals A. Well, technically, the symbols are interchangeable, sort of. But anyways, here we want to move the ES, which the ES is essentially where we're going to be storing the data, and we want it to be this at first because this is where the pixels are stored. So if you want to draw something, we'd have to draw it there. If you want to actually make it go to draw graphics, but if you run that, you can see that's not allowed. So we actually have to move into AX and then move AX into ES. Next, the TI will hold a position. We're gonna put 641 there for now, but we'll change it. And then the color is in AL. So if you do that, we see a color there. Yeah. And as you can see, we can change the color to be red or anything like that. So we got basic graphics. That's actually kind of cool. So now it's time to explain this, which might seem really weird. Okay, so essentially in a normal situation, there's just there's an X and a Y in 2D modern operating system. But in this, for now, we have just an X. We're going to change it to be an X and Y soon, but at the start, we only have just an X. So we could create a high level method, but I want to be low level for now. We're going to update it all to be higher level later. But yeah, anyways, it's time to explain the one dimensionness. So this is the 1D graphics. Usually in a normal computer, you'd use 2D graphics, which is this. We have basic points here. X is equal to 30, Y is equal to 5, and X is equal to 30, Y is equal to 10. It's a default computer. But in our operating system, which uses 1D graphics, keep in mind it will always, we're going to change it. But for now, when we want to create graphics without any, high-level method, we're going to be using 1D graphics. And this is examples of 1D graphics. The same exact points is X is equal to 3230 and X is equal to 6430. So only one coordinate. And we can compare these two positions that mean the same thing. So the window width is actually 640. And the y times the width plus the x is equal to the 1D position, right? So essentially we could take those 2D coordinates and plug them in. The y is 10, so you put that. The width is 640, so you put that. And the x is 30, so we put that. And we solve the equation, and we get 6430, which is the 1D position. So that's how you convert between 2D and 1D positions. Yeah. So that's essentially 1D explained. Anyways, let's go right back into what we're doing. We uncovered the graphics. What's next? A mouse. Okay, this is gonna be pretty cool. So, about this, I don't want my operating system to have a mouse. It's because, like, you'll hear a ton of videos, arguing that mouses are one of the worst cons because they make stuff slower. So, instead, we're gonna be using a ton of keyboard shortcuts, which might seem really confusing, but it's more efficient and also, like, it makes you focus only on your keyboard instead of having to, like, type on your keyboard and then move to your mouse. I think it's a pretty quick solution. So we're going to move to the next one, which is a window. And a window is what we are going to implement. So in order to draw a window, we actually have to draw a row. And this is quite easy. We could just repeat an instruction multiple times using that. And CX holds how many times we're going to repeat that. It fills in the first row. And yeah, that quite easily, that's already something that would work. And we could change the color. I'm gonna do this for window style. I don't know, don't blame me. And now we're gonna draw like a draw row function with it. That'll just take like some minimal arguments. Like it'll take the DI. I mean, I'm pretty sure it's just gonna do this. But it's gonna take in the CX. So this is gonna be quite long. It takes in ES, a DI, it expects it EX, DI, AX, CX. So CX could be whatever the width is. So if we draw the row here, it'll just fill up until there, right? And we're gonna add more to this because essentially, if we draw a row twice, and we do this, it'll keep on going. I want it to like go to the next row. So how you do that is I'm gonna take some registers that we don't use. So BX, right? BX is 320. Subtract the BX from the width we've caused. So I think we'll actually expect like a DX as the width, and then we'll move CX to be equal to DX. We subtract the BX to the DX, and we add that to the DI. Pretty sure that's the method. Wait, so I'm pretty sure it's at that, right? Oh, it's actually 640 because that's the length. Yeah, that actually makes it thicker, which is very good. That's exactly what we want. Now we can do this with 100, and we only filled the second row, so it's gonna look like. Dang, that's surprising. I didn't expect it to. Code that works when you don't expect it to. And we don't have to. Yeah, the DX is just staying still, so we could do that. And then we could like draw the row multiple times, like here, and we have a thick window, right? So I'm not gonna worry about repetitiveness. And here, we're going to give it 300 to cover approximately half the window. The direct half will be like 320. But I'm trying to make the numbers up pretty here, so don't blame me. And once we have this, the second part of the window is the so that basic stuff. And for that, we're actually gonna have to do something really interesting. So it's gonna be one of the longer parts. We're actually gonna have to create our own custom font. So for example, I'm just gonna each array, DW specifies that it's an array of words, which are 2 bytes. And first we put the length. So if there's one pixel to be printed out for the character X, we would put 1 here, and then we would just say 2 for we would draw this second pixel. So now we could actually draw the draw font. Right? So we have a draw font. And what it's gonna do is it's gonna be like print string actually. I'm not gonna copy it because that will not work. I mean, we'll have to do a lot of adjusting. So essentially, in the font, I'm gonna put it up here because it's easier to customize it, and it's gonna expect the SI to be the character, right? And then it'll just draw the font, and it'll load this SI into the AL. I think that's what it does actually. If you look at this, I already put it in my kernel. Actually, I took it away. Yeah. So I mean, actually, maybe I could do that. Yeah. This just loads directly into a font loop that will do about the same thing, but it's a 16-bit registry, so we actually have to do AX. Am I right? Yeah. So then, once we have that, well, obviously we're gonna jump font loop, right? And well, first things is we're gonna have to CX equal to the SI, and then we're going to loop the font loop. Actually, wait, you just do that right here. So you keep on doing that, and then you increment the SI, and I think you draw a pixel that's spot. So stars B. Da, 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 da. So now these are the arguments. We don't have a DX, and he will just give it a different unique color. So for the test.asm, we do this DI. Oh, what's AX doing here? So here we'll jump into the font loop. And if we're done, we return. And actually, maybe it's because call it. That's an AL. So let's call it 10. Um. Oh, we're gonna have to increment the SI. Also, can you like make this a bit more visible? I see something there. Like, wait, move it onto the next row. Yeah, easy. So now could I do 2 characters? Loop. Add SI2. Oh, also we have to actually load that. And then so you just saw an edited clip of me working, and yeah, I think we've done the custom font and the windows. So what's the next one? Key input at number VII, number 7. Yeah. So getting key input is pretty easy. Actually, for you, I already assembled a quick test version that gets character, and you can make out what I'm doing here. I could actually run this. I mean, I don't want to run this. I'm a 15. Oh, I think I actually So I actually created a script that would get my characters, and this should probably be in the like an examples folder. Read key, right? We should actually probably call it read key.asm, and in my kernel, it gets that back, bad boy back, and it has a window like usual. And the problem with keyboard input is that we need to write a custom font and have every single character there to do that. So essentially, instead of doing all of that, what I'm going to do is wait for a key press and then draw a character. So this is going to be really easy. All you have to do here is just wait. See? It draws it only when you press the key. So it doesn't activate outside of the operating system. But inside works. And I would like to experiment with different keys. Control, option, or command is not a key, but the arrows are. But if you like put the command with another one, that was Control C. I should probably do Control K, for example. That works. And like Option F, yeah. So as long as it has anything attached to it, and that is not its own key. It does show up in my Mac OS because the touchpad, but it's not a key press. But if I merge it with something, it's not the FN being called, like, yeah. And then if I use this computer operating system, so I'm gonna press an F key, but you can't press in like F key directly in Mac OS, because we have a touchpad. So what's my vision? Apple and Ventura 13.0 screen. Design a touchpad. Yeah, you can see over there that thing. So if you press the FN key for me, this key over here, then you get the F keys on the keyboard. So essentially, if I do like F and then I press the F6 through there, it's gonna do that. I don't think it's an operating system thing. I'm pretty sure it's the direct computer thing, sort of, something like that. I don't know. But my triggers in event on my PC, like on the computer, but the operating system won't notice. So, anyways, that is quite interesting. That's easy key input because we can't actually get like put the characters. Sorry, I wish you could actually. And the step VII/step 8 is a menu bar. And what I mean by that is, you see in macOS you have this. Now obviously my operating system, you can see it's like pretty Windows based, like compared with the Mac. Cause like some things I would agree with Windows more. Don't blame me. And the key input, when we're actually gonna be doing most stuff, the key input's gonna make a like cursor move and stuff like that. It's gonna like make the mouse cursor move, like print buttons, get buttons, do that type of stuff. So yeah. A menu bar. So essentially, 320 by 200, 640 by 400. I'm pretty sure it's gonna be by 400. So like, so this is gonna take a toll on your mind. That's the largest integer in the world. I mean, not the largest integer, but like, you get the idea. It even exceeds the bounds of my operating system. Of my, because 16-bit. Right, so we can't actually hold anything that large, which is a major problem, right? So in order to do that, I'm just too lazy to write every single zero and count them. I'm not stupid. Don't worry. You're in good hands. So the 640 by 400 display is actually too large to do something like that. So you know what that means? To just do something as simple as a menu bar, we're gonna need to switch to 32-bit protected mode, because the max value of 16-bit integer is 65535. 32-bit, 2 billion. That's why I want to switch to 32-bit protected mode. Also, just makes the system better. You get what I'm talking about. So it's actually time to switch to 32-bit protected mode. So actually, based on my investigations, it seems the best that a menu bar will be at the top. Wait, so here's a menu bar. And here's a window. So, we're actually not going to change the TI. I mean, okay, I think. Oh, so I still want to do like this and set it to 0. But, like, could I change the font? I mean, the color. So, I actually forgot what the color is set. I think it's an AL. Yeah, so AL's like 9. So I'm actually gonna say draw win. Right here I'm gonna see a line halt, so I'm gonna ignore that. And yeah, as you can see we have that. Could I change the color? Can I not change the color? Hello. Oh, it's an error right there. So yeah. Now E. Okay. So it's whatever we want the color to be. I'm gonna say it's green for now. Make it a little thick, boy. And yeah, that's good. The only thing is we should probably like push the DI or something. The reason I did that is so that we can pop into DI. Oh, wait, pop into the BX. Yeah, so just put it into the BX. Oh, and then we should probably add, put the add BX10 instead of that. And does that mean an X is an extra? Yeah, so now we have a menu bar which stretches the entire thing. And if we wanted to actually like do something, we would have to add text, and that's like a whole a lot of fonts. And the problem is this is like, yeah, so after here, like a lot of things started to get a little text based, font based, requiring on font. So I think the best method to do this is to do the fonts, and then actually after this, the video will end with a part 1. So the part 1 is gonna be like 1 hour or something like that. That's what I'm believing. And then in the next part, I'm gonna like continue with some more stuff. That's what I think is gonna happen. I might make it longer. So actually no, I'm not making it 32-bit, but with 16 bits, I created this. But now, here is where the actual test comes, because I have to create my own font, and that's going to be rough. So actually, I'm gonna say this is the end of the video, and I'm gonna post this video on YouTube. The next episode will be like the font and all of that. So like, yeah, because I know I haven't posted a YouTube video in a while. So anyways, that's it. Goodbye. And I actually will be posting this on GitHub, so that's a good idea. I should probably do that. So I'm gonna call this InfernoOS, and I'm gonna create the repository. We can do that. Git add everything. Hello. No. And then we can do all that. Take up some time, and now it has the whole thing. So, easy. I just got it posted, so I'm gonna put this in the description. Anyways, thank you for watching my video on the OS, and I'll be working on it in the next episode too. Thank you. Goodbye.